For weeks, the most important object in our solar system has been invisible, a ghost. Interstellar Comet 3I, Atlas, the messenger from another star, has been swallowed by the one thing in the sky more powerful than our curiosity, the sun. This was not a surprise, but a frustrating certainty of orbital mechanics. Around October the 21st, 2025, the comet, the Sun, and Earth moved into a precise alignment known as solar superior conjunction. From our perspective, 3I Atlas slipped directly behind the solar disk, vanishing completely in its blinding glare. This observational blackout coincided almost perfectly with the comet's most violent and transformative trial, perihelion. In late October, it made its closest, fastest, and hottest pass by the sun. For a comet, perihelion is a trial by fire. This is especially true for an interstellar visitor. It is being subjected to a level of solar radiation it has likely never experienced. We know 3I Atlas is rich in hypervolatile ices like carbon dioxide. The intense heating at perihelion would have driven the CO2 from its nucleus not as a gentle mist, but as explosive, high-pressure jets. This is a process of thermal shock. The nucleus's surface is cooked. Its pristine ices are processed, and the physical stress can be enough to crack the entire object apart. New fissures can open, exposing fresh, ancient ice from its interior for the first time. Or the nucleus could simply disintegrate, vanishing into a cloud of dust. We were blind to all of it. Now, in December, the wait is over. The orbits have moved on.
The cooking process may have changed.
Atlas is emerging from the sun's glare, set to reappear in our pre-dawn or post-sunset skies. The entire astronomical community is holding its breath, pointing its instruments at the horizon. The first observations are not routine, they are a damage report. The first, most urgent question is simple. Is it still there? The second is far more profound. It went into the fire as one object. What is coming out? The first photons we collect in December are for triage. This is the post-op. The questions are brutal and binary. First, did it survive? Second, is it intact? Facts and dates. We are not observing in a vacuum. We have a robust before snapshot, high-resolution images from Hubble, and critically, the data from the Mars Orbiter Fleet, MRO, TGO, during the October 3rd flyby, gave us a precise baseline for the comet's morphology, its shape, size, and brightness. Now, we compare. The very first observation is photometry, simply measuring its total brightness. There are two primary possibilities. It could be brighter than predicted. This would be excellent news. It would imply the intense solar heating did exactly what we hoped. It blasted away the surface crust, opening new, massive fissures. This would expose pristine, hypervolatile ices, like its signature CO2, from the object's interior, causing a dramatic and sustained surge in outgassing. We would be seeing a reborn comet, more active than ever, or it could be fainter. This is the fear. It could mean the nucleus armored itself. The surface ices baked away, leaving a dark, inert, and insulating refractory crust. Or it could mean the worst-case scenario. This brings us to the second test. Integrity. We need high-resolution images fast. Is the new image a single, sharp point source? Or is it a fuzzy, elongated cloud? A string of pearls like Comet Shoemaker-Levy 9? The CO2-dominated nature of 3I Atlas makes it a prime candidate for fragmentation. The explosive, non-gravitational forces of its jets, supercharged by perihelion, could have been enough to overcome the nucleus's own weak gravity, calving off large pieces or shattering it completely. This first after image dictates everything that follows. If it is a single bright object, we have a pristine laboratory. If it is a cloud of debris, the mission changes. We are now performing an autopsy. All reports from the first nights of observation will focus on this simple, profound before and after. Assuming it survives intact, the real work begins. Analyzing the dust it's now shedding. It survived. It is intact. Now, the real forensic investigation begins. And the first tool we have is not a complex spectrometer, but the simple, powerful geometry of the solar system. We are about to exploit a new weapon, the phase angle. The phase angle is the angle between the Sun, the comet, and the observer, Earth. Sun-Comet-Earth. When 3S Atlas was inbound, before its solar conjunction, it was on the far side of the Sun. We observed it at a small phase angle. We were essentially front-lighting it. Now, as it reappears in December 2025, its orbital position has changed. It is moving away from the Sun, but we are seeing it from a completely different, wider angle. We are moving from front lighting to side lighting, and eventually backlighting. This change is everything. How an object scatters light is completely dependent on this angle. Think of motes of dust in a dark room. If the sunbeam is shining at you, small phase angle, you barely see them. But if the sunbeam is shining across your view, large phase angle, every tiny particle of forward scattering dust lights up. This is our first, most crucial test of the perihelion passage. Before perihelion, we assumed the comet's dust was pristine, likely large, fluffy, complex aggregate particles. These grains are good at backscattering light, which is what we saw when it was inbound. But the trial by fire at perihelion, the explosive CO2 jets, the thermal shock, was a violent event. It very likely shattered those large, fluffy grains. It may have created an entirely new population of tiny, submicron, smoke-sized dust particles. This gives us a clear, immediate test. As we observe 3S Atlas from its new, wider phase angle, we simply measure its brightness. If the comet's brightness surges dramatically at high phase angles, it confirms that this new population of fine, forward-scattering dust now exists. It is definitive proof that the comet's physical properties were altered by the Sun. This simple photometric measurement is the first clue that the cooking process was not superficial. It was transformative, changing the very texture of the material this alien visitor is shedding into space. We've confirmed a change in the dust size distribution. The phase angle data from the first nights of observation shows that the comet, after its trial by fire, is now shedding a new population of fine, forward-scattering dust. But this is only half the story. The next urgent question is about the dust's texture. Has the Sun physically cooked the grains themselves? For this, we use a new tool, polarimetry. Sunlight is unpolarized. Its waves vibrate in all directions. But when this light scatters off a particle, like a mote of dust or the surface of a lake, it becomes polarized, forced to vibrate in a preferred plane. This is the glare that polarized sunglasses are designed to block. A cometary dust grain is a tiny polarizing filter. The way it polarizes light reveals its deepest physical properties, its size, shape, and, critically, its fluffiness or porosity. A fluffy, porous aggregate grain, like a speck of soot, polarizes light very differently than a solid, compact, annealed grain, like a microscopic marble. We have before data, pre-perihelion measurements of 3I Atlas, though unconfirmed, suggested it had extreme negative polarization. This is a known, though rare, signature for extremely pristine, porous, fluffy grains. It was a tantalizing clue that this interstellar visitor was made of a uniquely primitive, unprocessed material. The perihelion pass was a powerful annealing event. The intense solar heating would have been strong enough to vaporize the volatile ices binding these fluffy grains, causing them to collapse, melt, and re-solidify into more compact solid particles. This gives us a clear prediction. As we re-observe Sun-Comet in 3I Atlas in December, we will not just measure its brightness, we will measure its polarization. If the after polarization curve is different, if that signature of extreme negative polarization is now gone, replaced by a shallower curve, we will have definitive proof. We will have watched the sun's heat fundamentally change the physical texture of this alien material. We are building a forensic before and after portrait. The phase angle told us the grains were shattered into smaller sizes. Polarization will tell us their structure was compacted. We are one step away from the final question. Did its core chemistry change as well? We have the dust. The phase angle and polarization data have given us a clear before and after picture of the physical grains. We know they were shattered and compacted by the sun's fire. Now, we hunt the engine. The gas. We must retake the comet's chemical fingerprint, and this is the highest priority for JWST and ground-based observatories. The before picture was tantalizingly alien. JWST observations confirmed 3I Atlas is overwhelmingly CO2 dominated. Its CO2 to water ratio was extreme, a key non-solar signature. Separately, unconfirmed reports from high-resolution spectrographs hinted at another anomaly, the presence of nickel, Ni without iron, Fe, a refractory puzzle that defies solar system chemistry. The perihelion passage was not just a physical shock. It was a thermal one. This intense heating likely peeled back the comet's outer layers, the crust that had been processed by millennia of cosmic rays. It may have exposed a fresh, pristine mantle from the comet's interior. This new, exposed surface could have a completely different chemical mixture. This gives us two immediate critical tests for the first after spectra in December 2025. First, the CO2 to water ratio. We point JWST and Hubble to measure the OH water proxy back at the comet. If the CO2 dominance continues or increases, it means the comet's engine is just a more powerful version of its old self. But what if that newly exposed mantle is rich in water ice, which was frozen solid before, but is now vaporizing? If so, we will see the water, OH signal surge. The comet's alien CO2 signature might dilute, making it appear chemically more solar-like than before. Second, the refractory metals. We point ground-based spectrographs like the VLT back at the coma. Did the intense heat finally vaporize the iron? We will check for that Fe signature. If it suddenly appears alongside the Ni, it might solve the anomaly. If the Ni signal remains alone, but stronger, the mystery only deepens. We are not just looking at the comet. We are performing an autopsy on the material it just shed, comparing the chemical signature of its cooked surface to the pristine interior it has now, perhaps, finally revealed. This is the synthesis. We are not just observing an object. We are, for the first time in history, observing a process. We have been given a unique gift, a before and after portrait of an alien artifact, forged in a distant star system and reforged by our own. The before data, gathered from July to October 2025, is a snapshot of its pristine state. This is the 3I Atlas that drifted for millions of years in the interstellar dark. Its CO2-dominated engine, its fluffy, porous dust, its bizarre, Ni without Phi anomaly, this is the baseline. This is the chemical recipe of its home. The after data, gathered from December 2025 onwards, is the autopsy. The phase angle data, Part 3, reveals the shattered dust. The polarization data, Part 4, reveals the compacted, cooked dust. The new spectra from JWST and the VLT, Part 5, reveal the changed chemical engine. We are watching the comet's identity bifurcate. We are answering the question, what happens when a pristine relic from there meets the fire of here? And there is one final crucial measurement to make. The observational campaign does not end in December. As the 3, Atlas continues its outbound journey, its geometry relative to the giant planets provides one last gift. On March 16, 2026, its trajectory will bring it into a precise alignment relative to Jupiter. We will use Jupiter's immense gravity as a gravitational pin. By precisely measuring how the giant planet's mass bends the comet's trajectory, a science called astrometry, we can calculate its exact path. We then compare this observed path to a purely gravitational model. The difference is the non-gravitational acceleration, the precise physical push of the comet's own jets. This gives us the definitive after measurement of its engine's power. We can then compare the outbound jet force to the inbound jet force. If, as we suspect, the post-perihelion force is significantly stronger, it is the final, irrefutable proof that the sun's fire opened new fissures and fundamentally, physically, and permanently transformed this interstellar visitor. Atlas will not return. It will carry the scars of its solar passage back into the void. But we will have its complete story, the message it arrived with, and the mark our sun left upon it.